Welcome everyone. My name is Gianmarco Iodice. I'm the chair of the tinyML global meetup groups and also tech lead at ARM for the ARM Compute Library. Today I have the great pleasure to moderate this talk where Huang and Pierrick Autret from STMicroelectronics we talk about NanoEdge AI Studio, so all on-device anomaly detection for Industry 4.0. So before we start with the presentation, I'd like just to give you some information about the tinyML Foundation. But first of all, I want to thank all the tinyML strategic partners that are making this event and all the other events in person, virtual, available to everyone. So in particular, I like to thank AZ, Arduino, ARM, BrainChip, Edge Impulse, Embed UI, Efficient, Green Waves Technologies, Gravity Inc., HiMax, ImageMob, Infineon, Innaterra, Not AI, NXP, PNG, PMIC, Pauline Technology, Qualcomm, Renesas, SNI Electric, SensiML, Sony, Silicon Labs, STMicroelectronics, Synaptics, Synchance, and TDK. So, as I said, I'd like to give you a few information about the tinyML Foundation. The tinyML Foundation is behind all the events around the tinyML community, a community that is growing every month with almost 19K members in the meetup group with 49 groups worldwide. And here is a recommendation. I mean, if you haven't joined any meetup group yet, I recommend to join to spread the knowledge in your country about the possibilities with tinyML. But if you don't have a tinyML group in your country, in your region, you also have the opportunity to create one. You can be in contact with us to see what we can do. So, but the community is not just on Meetup. We also have a growing community also on LinkedIn with roughly 4K members and over 14K followers there. So, a crucial resource for all the tinyML enthusiasts, researchers, developers, or anyone is experimenting and playing with tinyML is certainly the YouTube channel. So in YouTube, we host all the presentations that we have with the tinyML global talks. And also with the other tinyML initiatives. So this is absolutely the place where you can learn from the experts and novel techniques to enable tinyML or machine learning on low-power devices, and also be always updated about the recent advances in this field. And here we are. So I have the pleasure to introduce Huang. Huang is a data scientist and researcher with expertise in embedded machine learning. He holds a PhD in electronics from INSA Toulouse in France, earned in 2015 and completed a postdoctoral research fellowship at Politecnico di Torino in Italy in 2016. As the former chief data scientist at French startup Cartesian from 2017, he played a pivotal role in the development of NanoEdge AI Studio, an innovative platform for on-device machine learning at the edge. It is with my pleasure to introduce you, Huang. But Huang won't be alone today because there is also Pierrick Autret, who has been Artificial Intelligence Solutions Manager in STMicroelectronics Microcontroller Division since 2019. With a master's degree in engineering, specializing in embedded system from the École Polytechnique, and master's degree in marketing, economics, and management from IAE in Provence. Sorry if I didn't pronounce properly. He began his career as a hardware product owner on STM32 series before developing the ST software offering. So again, thanks everyone for attending this talk, and I leave Huang to start this talk.
Firstly, thanks for Gianmarco for the introduction. I would like to express my gratitude for the invitation from tinyML and the excellent organization by Olga for this talk. Last year, I had the opportunity to present a poster of the same topic at the tinyML EMEA conference in Amsterdam. It was a wonderful experience for me, and I had a lot of very helpful exchange with the community. Today, I'm excited to be here with my colleague Pierrick to present our on-device anomaly detection solution for the Industry 4.0 and our auto machine learning platform, NanoEdge AI Studio. Yeah, my name is, you can call me Henry, and I'm a data scientist at ST. For the past 7 years, I have been working on the algorithms for the NanoEdge AI project. I'm currently based in Paris.
And I'm Pierrick Autret, I'm Product Marketing Manager. I'm based in Rousset, south of France. So basically, today we will talk about Edge AI. We all know the advantage of Edge AI. Just a quick reminder, thanks to the fact that we are running the inference locally on the edge, it's helped to reduce the latency for smart products. It doesn't require any connectivity, and if there is some connectivity features, it's allowed to unload the bandwidth compared to sending all the raw data for inference. It's also increased the security and the privacy by design, removing the backdoor and so on. And finally, last but not least, it's helped running the inference on the power effective MCU allow to create a solution way less power consuming. So it's allowed to create some sustainable products. This is because all these advantages that ST have been working to deploy this technology for over 10 years. We are a member of the tinyML Foundation since 2019, but our journey started before. In 2018, our first major steps for the developers was enabling the porting and optimization of pre-trained AI model onto the existing range of STM32 MCUs, thanks to the tool STM32 CubeAI. Later, we add the same capability to the automotive MCU, but also to the sensors themselves from 2022. Today, we are going further in with the disruptive techniques. One of the main challenges in deploying Edge AI solution is to have a generic and accurate model, which will be efficient for all the equipment where the model is running. And actually, this is not easy. Let's take an example with the pump in a factory. Even if all the pumps are the same on the data sheets, we know that their behavior will be different from one to the other because the usage, because the environment, and so on. Today, we will talk not only about the inference on the edge, but also about the training on the edge. The on-device learning capabilities in our offer allow to fine-tune AI model for every single product and to reduce the false positive and the false negative. These techniques already help ST, but also ST customers to reduce some equipment downtime down to 220%, which is huge, actually. Indeed, as you know, going from preventive maintenance to predictive maintenance allow to stop equipment unnecessarily and allow to manage the production in a smarter way. So I will let Henri explain a bit more in detail about how it works.
Thanks, Pierrick. The first part of the presentation is about the conception of the algorithms of our all on-device anomaly detection solution at the edge. To ensure that on-device models are efficient, they must be designed with resource limitations in mind. This is because hardware at the edge, like the MCU, is often limited in comparison to servers. There are various levels of edge intelligence or on-device. That means both learning and inference are at the edge is the most flexible and independent in terms of resource usage. This approach can maximize the advantages of Edge AI with zero data transmission. However, developing new algorithms and logics is necessary. Our approach to anomaly detection in industry machines involves 3 key steps. First, we identify the main requirements for industrial predictive maintenance, such as security, cost saving, autonomy, sustainability, and flexibility. Next, we define the algorithm criteria, which outlines what the algorithms need to achieve as functions to meet the needs of industry, which are mentioned in step 1. And finally, in step 3, we implement on-device learning on the individual machine using algorithms that meet all the criteria in step 2 to have an adaptive AI model that is trained on device to the specific machine. For the industry predictive maintenance, of course, we have the concerns of security, sustainability, autonomy, and cost saving, which make the Edge AI a good solution, but not enough, because in this application, the Edge AI model must be flexible enough to adapt various situations, such as different machines, functions, environments, and updates or maintenance over time. It's very common that the test results in the laboratory is different from those in real-world implementations. And another difficulty in the practice is that it's not easy or not possible to obtain enough anomaly signals in the real machines. To address these challenges, Edge AI models need to be universal and adaptive. We need to create the individual AI models for each machine. These models can adapt to different machines and environments individually and incrementally. That is why we need to define additional criteria for our on-device learning algorithm. The first criteria of algorithm is that our initial AI model starts with an empty model without any pre-trained knowledge. It's not like most other on-device learning solutions. This approach helps us to economize the development cost and maximize adaptivity for different situations later through on-device learning. Then, for the on-device learning, the model is trained directly on device using local sensor signals that we merge from the industry machines, such as accelerometers or current sensors. The AI model gathers knowledge incrementally to become better at detecting potential anomalous behaviors. One important advantage of our solution of this approach is that no additional memory is required, because each learning signal is used only once to update the AI model and then removed immediately after each update. So we do not need to allocate additional resources for memory storage. Once the AI model becomes mature, we can start the inference step for the same machine using the trained AI model. The output of this step is the inference results, such as the anomaly score. Besides, our solution provides the flexibility to run additional learning cycle if something new happens, such as the learning of some new functions. It's really convenient for the real implementation. If we want, we can also switch between learning and inference. That gives the possibility of the model to adapt to all possible evolutions over time. Finally, to have an adaptive on-device learning, as we have demonstrated, we need to respect these 8 criteria, which present a significant challenge for the selection and conception of algorithms for AI models. Well, there are already some examples of incremental calculations, such as calculating the average value. These 8 additional criteria introduce new restrictions that require careful consideration, like the zero pre-trained model, the possibility to switch the learning and inference, no additional memory to save the data, and the tolerance for small number of anomaly signals during training. All these criteria present additional restrictions and technical difficulties, but at the same time, they present also the huge advantages of our solution, because they are all based on the real needs of the application. We use very often neural network for AI, as neural networks may forget learned information when trained on new data. The catastrophic forgetting problem of neural network is a significant issue in on-device learning with limited resources. To address this problem, we have developed 5 incremental algorithms based on different statistical features that are better suited for on-device learning at the edge, while still meeting the very challenging criteria outlined here. Here are 2 algorithm flowchart examples. In the examples, the first step of algorithm involves signal processing. The second part involves our on-device learning methods. We have created different blocks of algorithms that can be combined to adapt different data types and applications. I want to share with you a video which is made with the help of MATLAB. This video demonstrates how it works. One of our 5 on-device learning methods, micro machine learning. This method is particularly useful for learning different categories of behavior. During the learning process, the model first identifies if the data is in a known category before using it to update its knowledge. We can have multiple categories of behavior, and the colors in the video show the probability of anomaly in different zones. Once we have a mature AI model, we can use it for inference. We compare the new signal with each category, and we select the category where the new signal has a lower anomaly score, and then we use this score for the final inference. We have presented the advantages of on-device learning. Does it work? And in which situations should we use it? The data is the foundation of all AI solutions, and we use regular and abnormal data sets from multiple machines for training. We can obtain 2 AI solutions. The first is on-device learning, which is an adaptive model. And the second is classification with a static model. To test the accuracy and flexibility of our two AI solutions, we will not only test the machines used for training, but also machines that were not used during training. This approach allows us to evaluate the ability of both methods to adapt to new and different machines and environments. In our test, we used 3 different fans and used their sound as the signal. For the machines used in training, we observed that the classification approach works better than on-device learning. However, for a new fan that was not used during training, the on-device learning approach worked better. We observed similar results when we switched the machines into 2 groups. And here, the classification approach did not work at all for a new machine, where on-device learning always provided accurate results. We believe that this is due to overfitting. It's very common in the situation where the model is trained on a dataset that does not represent the full range of possible conditions. This can result in the model being too specialized to the training data and not being able to generalize to new or different situations. The test results highlight the flexibility of on-device learning. The classification approach may perform better in situations where the data is stable and well-defined for known individuals. In contrast, on-device learning is more adaptive to new and changing conditions, allowing it to provide accurate results, even in situations that were not used during training. So, if the data set is sufficiently representative of all possible situations or the dispersion, then the classification approach may be the best choice. However, if the model needs to be flexible and adaptive to changing conditions and new machines, then the on-device learning approach may be more effective. By selecting the correct approach based on the specific needs of the application and the nature of the data, we can have a good anomaly detection solution. Our development platform, NanoEdge AI Studio, provided by ST, is a perfect tool to simplify your choice and the development. We will provide you more details. Please, Pierrick.
Thanks a lot, Henri. So, as Henri said, actually our goal is to make the creation of Edge AI solution simple, rapid, and more cost-effective than any other technology. This is why we are bringing this research that Henri mentioned in NanoEdge AI Studio. Actually, this tool is a tool which will cover numerous use cases because we can see that our customers are creating ever more intelligent products. We are proposing 3 main families of algorithms in the studio to cover almost all the use cases on the market. So first of all, we have the anomaly detection to detect any abnormal behavior, to prevent any failure, to detect any drift. With the on-device learning capability that Henri mentioned, we can create really fine-tuned and an accurate solution to alert if an anomaly occurs on any kind of equipment. We have also the classification, so this is straightforward. To keep the same example in predictive maintenance, classification will allow to classify if an anomaly is a bearing issue, a misalignment, clogging problem, or whatever. But we can think about way more use cases. For example, if you take a smartwatch, we can add an advanced feature running locally on the watch itself, saying, okay, someone is walking or running or swimming and so on, to, let's say, to create some advanced feature to the user. And last but not least is the extrapolation, the regression models. So the goal of the regression model is to predict future states. I mean, more precisely, is to extrapolate states from well-known values. For example, we will take the use case of the washing machine here. This is a proof of concept that we have created in ST, where we are approximating the weight in the drum, the amount of cloth in the washing machine, without any sensor. We're just taking the value of the current from the motor control, which will run the drum, but also the speed of the drum. And because we make a learning on several, let's say, correlation between the current value and the weight, we can extrapolate other values. I will come back on this use case a bit earlier. The thing is, we know that the AI development workflow is not straightforward for every embedded developer. There is a lot of steps from the data acquisition, data cleaning, model selection, the training, and the model deployments on the MCU. Because we want to make Edge AI accessible for every embedded developer, we have created NanoEdge AI Studio, which will support every developer from the beginning to the end of this workflow, from the data preparation to the model implementation. So basically, for example, for the data preparation, we have a tool called the sampling finder. This tool allows to find the best sampling frequency and the best buffer size based on your use case. Once the parameters are defined, you can use another tool which is available in the studio, which is called the data logger, which will allow you to create in a matter of few clicks a data logger by selecting a board in the list of STM32 development board, and the sensor that you want to use on this board. And then you will generate the data logger, and you just have to drag and drop the file in your board to start collecting your data. A third tool, which is available in the studio, is the data manipulation to clean and to sort your data, because we know that a good data set is really important to have a good model. Then, when you have a complete and clean data set, the core of the studio is the benchmark tool. So actually, the benchmark, we benchmark hundreds of thousands of combination. When I say combination, it's model, machine learning model, but also the hyperparameters and the preprocessing, such as an advanced feature extraction and so on. We will benchmark in a matter of minutes, thousands and thousands of combinations to find the model and the parameter which are matching your project. So here we have sensor agnostic. It means that you can use any type of sensor. The thing is, we want to keep it as tiny as possible, I mean, the size of the model. So we are not supporting a camera yet, but any other kind of sensor. And when I say tiny, I mean a few kilobytes of RAM and a few kilobytes of flash, starting from a couple of kilobytes of RAM and flash for simple libraries. So that means that you don't have to add an MCU, an hardware to your solution. You can implement the machine learning model on your existing hardware if you have some space available. Then, when your library is found, when the model is ready, you can download it and integrate it to your embedded project. So, and just you will call it like a simple function. Edge AI-based products are a reality today. So there is already a lot of products on the market with Edge AI running on it. For example, this aftermarket solution from Oxytronic add intelligence on any equipment by learning the normal behavior from various sensors, vibration, pressure, temperature, ultrasound, and then send an alert to a dashboard through optimized connectivity, such as Bluetooth and ZigBee function. Actually, it would have been a nightmare for Keytronics to create a huge generic model which will be able to detect anomaly on pump, on motor, and so on. The fact that we can learn here directly on the sensor allow to have a tool which will have an optimized model for this specific use case. So anomaly detection algorithm from NanoEdge AI Studio help every industry to create predictive maintenance solution and to optimize their maintenance strategy. The studio helps to create new advanced feature, but also help to improve existing solution. For example, as I previously discussed, the regression library can help to accurately approximate the amount of cloth in a drum without any additional sensors, just with the current and the speed of the motor, if you remember. This is not a new use case, actually. My machine washing does the job. However, washing machine maker have some difficulty to create accurate solution with traditional algorithm. Thanks to NanoEdge AI Studio, some main white good manufacturer went from 500 grams of uncertainty to almost 100 grams of uncertainty, which is closed weight solution. So here, the regression algorithm help to reduce the uncertainty and to, let's say, increase the accuracy of the solution. It has been a, let's say, a blocking point for some of our customers, which can now take benefit from this solution to optimize way much the washing cycle and save more energy and save more current and water in their washing machine. The next example is interesting because Edge AI is being used to something that is not at all obviously at the first glance. The application is measuring the tire pressure in an e-bike without any sensor in the wheel. It's done by monitoring the current consumption of the motor and the speed, once again, to assess if the tire needs additional pressure. This algorithm has been developed by a major e-bike maker and run on an M0-based STM32G0, so really cost-effective microcontroller. This is very remarkable here because it has been developed without any new hardware in the e-bike or in the tire, in the wheel themselves. Moreover, virtual sensor help company to reduce their cost of BOM. So it's really interesting use case, I think. This is few examples of the application we can address. Obviously, there is way more application. For example, people presence detection, people counting, gesture recognition. There is a way more on our website, stm32ai.st.com. And just to sum up, the studio proposed the state-of-the-art of the machine learning to every embedded developer. So with more than 10 patents filed, we want everybody to access to this technology, which is Edge AI. So you don't need to have data science skills. You don't need to have machine learning knowledge to take benefit from this technology and to add advanced feature to your products from today. So by the way, we recently announced that the studio and the right to go in production with NanoEdge AI library on STM32 is completely free of charge. And we are officially supporting every Cortex-M based hardware on the market for dual sourcing purpose, for example. So feel free to try the studio today on any type of application. And thanks for your time. And feel free to ask any question if you have some.
Thanks a lot for this very interesting presentation. I also have some questions, so be prepared. So no, but there are also quite a lot of questions in the Q&A box. I'm not surprised because there are a lot of things very interesting for the tinyML community. Okay, so let me open the Q&A box. So the first question is the following, and you can also read the question here. So does it mean that initially these machines equipped with SD microcontrollers have no AI capability and hence are not smart when it comes from factory, and with time they become smart?
Yeah, so I will take it, Henri. I don't know if you were responding, but you're mute. So sorry, I started. Actually, yeah, the STM32 MCUs come without, let's say, AI function in it from factory. So the advantages and the purpose of using NanoEdge AI Studio is to add this AI, let's say, functionality to some standard MCU. So we are supporting every MCU, as I was mentioning, from the little M0 Cortex to the high-end M7, for example. And we don't need to have some AI dedicated MCU to run it.
Okay. So I have a question. So what data type do you use for doing on-device learning? Is it floating point arithmetic or is also integer arithmetic?
So the question is about how we do the on-device learning, which kind of algorithms we choose, or
is the data type? Are you using integer arithmetic? Are you using floating point arithmetic?
floating points?
Okay. Floating point arithmetic. Thanks. Okay, go to the next question. So can on-device learning be combined with some pre-recorded, pre-collected data? So the base of the model is pre-programmed beforehand, but some part of the learning is happening on device in runtime. I believe is about fine-tuning, right? So you have a model and you want to fine-tune. Is it possible?
Yeah, of course. It's all because we have actually in our model we propose the possibility that we start from zero. Why? Because it's the way we think in the real implementation is the most flexible for more implementations. But we also have the possibility because what we do today is just we use the data to update the model. So we can always, we have two choices, start from zero or start from something already pre-trained in the laboratory, but it's one option.
Just keep in mind, and I think, thank you, Henri, for the answer. I think it's important to precise that even if you use the on-device learning, let's say tomorrow to create to train your model, and the conditions are changing. So I mean, I don't know if you're working in viscosity of fluid or something, and because it's cold today, the viscosity is not the same that during the summer. You can retrain the model in 6 months without losing the knowledge that you acquired before.
Okay. So and from this I also understand you basically update the weights and you will have some parts that will store these values in Flash, I believe. So you do the calculation using the SRAM, but once you need to update the weights, you're going to put in Flash to keep it say forever. Is it correct?
Yes, what we save is just the model. So we don't save the data beside. Okay. Yeah. So every time we have the data, it just used to update the model. So the model is always saved in the Flash. Yeah.
And the weights that you update are also stored in Flash. So the adjustments for these weights are also stored in Flash. I believe so. Or...
No, for us, the only thing we save in the Flash is the model. Yeah. Oh, I don't know if every time we have a new model, of course we don't save the previous version.
Okay. So I probably can take this question is about, can you share the presentation today? Maybe today, no, or maybe late today, but tomorrow for sure. This presentation is recorded, will also be available on YouTube. Okay, the next question is, can a PID controller be trained somehow with on-device learning?
We don't really have the application about the PID controller. Why not? Yeah. We can try with the NanoEdge AI Studio.
Actually, this is a really good question. So we have some solution for motor control, obviously in ST, and we are collaborating between a AI solution group and a motor control to find some advanced solutions. So today there is not PID tuning solution on the shelf, but this is a question that we also had in mind, and we are discussing about it and trying to find some way to optimize motor control. But today there is nothing on the shelf. But we can, if you have a project, we will be very happy to brainstorm with you.
Thanks. Okay. Do you have support for random forest training in Edge AI Studio? Can random forest be trained on device at runtime?
Actually, now we have five different on-device learning methods. There's not the support for the random forest training on device, not yet, but I think that could be a solution in the future. Why not?
Yeah, random forest is really well famous model. Let's say in the five model that Henri mentioned, most of them are proprietary. So we have patented these anomaly detection models, which have been built by ST.
Okay. Not sure about this question. So Edge AI does Edge AI Studio include also tinyML binaries? So maybe some tinyML models. Do you have pre-trained models, for instance, in the Edge AI Studio that people can play with?
No, now we don't have this kind of. That means we have already the model is already trained for use directly. Means that?
Well, I'm not sure. Maybe if the
because today the studio, yeah.
Yeah, I'm not sure about this question. So maybe if this person can elaborate a bit more on this question, we can try to answer live. So I go to the next question, which is, I guess the on-device learning requires floating point unit working with AutoGrad, which would exclude those IoT devices without floating point unit. Is it correct? Or does ST have an integer-based learning algorithm? This is based, I think it's quite similar to the questions I asked before.
Yes.
So from what I understand is floating point arithmetic that works also without floating point unit.
Yeah, without floating point unit, I think it works.
Yeah,
sorry, because I'm not really the guy of the hardware. In my knowledge, I think it works with is floating point, but it's not. I'm not sure it's necessary the floating point unit.
In theory, well, probably I can jump. In theory, it's not strictly necessary. It can be software emulated. Of course, what you're gonna lose is the performance. I mean, it's not going to be extremely efficient, but it can work.
Yeah.
Okay, thanks. So what is the generic approach to deal with high-level noise for on-device learning? Are there any special techniques suitable for acceleration sensors?
I'm not sure I understand the terms of high-level noise. Yeah.
Yeah.
In this question.
So maybe here we are talking about, so let's assume we have sensors and they have noise quite noisy, with noisy signals. Are these algorithms robust enough to deal with noise, or do we have any filtering algorithms?
Yes, we have some feature in the frequency domain, and what we do, because it's very interesting for us, because in our implementation in different environment, it's not the same noise level, even for the same machine. For example, in the laboratory and in the real implementation. So that's why our solution has the advantage to adapt the noise in the real environment.
Okay. Thanks. Okay, so is the source code parameters of trained models available or only binary? How ST protects their models to be used with microcontrollers of different vendors?
So actually, we are proposing from the free tool, not the binary, but not the source code. So that this is the library, the .h either and the .a files. So you can implement it in your embedded project. We can provide the source code, but it's done only for, let's say, under particular agreements under NDA, because as I'm mentioning, there is some patents. And this is responding also to the second question, which is how STs predict their model, because we are not proposing the C code from scratch, let's say, from initially. And the model are optimized for STM32. So they're built for STM32 and run perfectly on STM32, but we are supporting every Cortex-M on the market. So basically, this is something which is explained in the SLA of the tool, that you can go in production for free on any STM32, and there is a specific agreement to go in production on different vendors if it's not a dual sourcing or something. So this is a case-based case state discussion.
Thanks. Okay. This on-device learning, is this on-device learning limited to time series signals, or is also adaptable to frequency domain signals?
Yes, it's a very good question, because for us, I have presented in the demonstration, like the animation is the time series signal from the accelerometers. But of course, as the algorithms, because we have different, as I have presented, we have different blocks of algorithms. It contains the different data signal processing and different AI models. So different algorithms and different combinations can adapt different types of the different natures of data. So of course, our solution is not only for the time series signals, and also for the other kind of, like here, the frequency domain features, or just the only features with different single. For example, we have several different sensors. So it's multivariate problem. We can also find the solution with the studio.
Okay. Thanks for your answer. And before I forget, because I'm not sure we're gonna address all the questions, because as we could imagine, actually, there are many questions, because the presentation was absolutely very good. And also quite a lot of technical details that we want to discover. But this conversation does not stop here. So because we also have the meetup forum where you can ask questions related to this talk directly to our speakers. And of course, they will be more than happy to follow up with you on the meetup forum. So I'm going to continue with some of these questions, so that I can see here on the Q&A tab. Have you used this approach to evaluate battery consumption in different environments? As an example, how microsolar impacts polling frequency? Just to give an example.
So good and bad news. The good one is, yeah, we can definitely improve, let's say, the battery management thanks to this tool. We have some work on the state of charge and state of health of the battery. The bad news is we didn't study the solar impact polling frequency specifically, but once again, we have a lot of people really curious about new, let's say, new use cases. So we can once again work on dedicated projects, but it can and it does optimize the battery management system.
Thanks for your answer. So, with on-device learning from scratch, how Anomaly is creating the actual online machines? How is data labeling done?
Yes, maybe.
Yeah.
Yeah, because for us, it's a very good question because it is also what we meet this kind of requirements in the real application, because in the industry, it's not as I have mentioned, it's not often or not possible to have the anomaly signals. So what we can do, we can have the test in the laboratory, and then we create the AI solution and we implement in the industrial environments. So in this situation, in the laboratory, of course, we have all the possibility to simulate all kinds of anomalies. So that's the interest or the advantages here for the on-device learning solution.
Thanks for your answer. I will probably take the next one and we'll continue with the end of this presentation. So we won't address the other questions, but please follow up on the Meetup forum to ask also these questions to our speakers directly and share the answers with other people. So the next question is about, is a model chosen from a fixed pool of models, or is the machine learning model topology adapted to the characteristics of the logged data?
So that's a good question. I don't know if you want to take it, Henri, but actually, when I was mentioning the fact that we want to propose the state of the art of the machine learning, is because, yeah, we are benchmarking, let's say, the combination of model which are already defined. So there is a pool of models in the studio, and we are, let's say, cross-validating between the model and the different hyperparameter and different preprocessing to find the, let's say, the flow with different brick of preprocessing and different model and different parameter to find the one which fit the best. So this is a poll. We are not building the topology of the model live, but we have 2 or 3 releases of the studio every year update. So we are increasing the number of model to keep the tool at this state of the art, actually.
Okay, so
thanks to new research and new patents also.
thanks for answering this question. That was the last question that we can address today. But as a reminder, with the conversation will continue on the Meetup forum, where you can ask as many questions as you want to our speakers. And on behalf of the tinyML Foundation, I want to thank our speakers because it was absolutely a very good presentation, and also people really appreciate it. I know there are very interesting questions, so that I like to see the answer, honestly. But unfortunately, given the time, we cannot address all of them today. So thanks again. I'm gonna just present a few more slides for the end of this presentation. Okay, again, I want to express my deep gratitude on behalf of the tinyML Foundation to our strategic partners. They are committing for making these free events available to you worldwide, virtual, in person. There are a lot of and more events coming, and the best way to learn about the events and the is actually subscribing to the meetup or on LinkedIn. You can also visit our website to learn more about the events for tinyML. So I want to thank in particular the executive strategic partners, which are Qualcomm, Synchant, the Platinum strategic partners, Embed UR, Sony, the Gold strategic partners, which are ARM, Edge Impulse, Infineon, Innaterra, Renesas, STMicroelectronics, Synaptics, the silver strategic partners, which are AZIP, Arduino, BrainChip, Efficient, Greenwaves Technologies, Gravity Inc., Himax, ImageMob, Note AI, NXP, PNG, PMIC, Pauling Technology, Schneider Electric, SensiML, Silicon Labs, and TDK. And with this slide, we're gonna end this presentation. And again, thank you a lot, he and Pierrick, for this brilliant talk. I'm looking forward to see your answers to the remaining questions in a Q&A tab. And with this, I'm looking forward to host another tinyML talk with you. Have a good evening. Have a good morning. Bye-bye all.